Hello guys, this is CodeNCode and this is third lecture of FFT. Okay, so this is FFT part 3.1 because I've divided the whole lecture into two parts because we have to go through a lot of things, right? And the lecture will be just huge if I try to explain everything in a single lecture. All right, so let's get started and let's see what we are going to learn in this lecture. So let's start with the topics that we are going to cover. So we'll start with the polynomial evaluation because that is the most important part that we need to look at, and we'll see the how we can optimize, right? Because we already know how we can evaluate the polynomial, but the important part is the optimization. So we'll see that how you can do that, right? And then we'll learn about roots of unity and how it helps in optimization of polynomial evaluation. And this is the reason why we are able to achieve n log n multiplication. My bad, n log n time conversion or evaluation of polynomial from uh, coefficient form to value form, right? Then we'll also learn about the evaluating, basically finalize the DFT, that is discrete Fourier transform, that evaluates polynomial in n log n time. We'll see the whole algorithm, and finally we'll learn the inverse DFT that does the job of converting back the value form of a polynomial to coefficient form. That is what we want, that is inverse DFT. We'll have a look at that also, right? So let's get started. So we have already seen in the last lecture, this is what the structure of FFT looks like. We have two polynomials that we want to multiply, ax and bx, in coefficient form. We'll use discrete Fourier transform, basically evaluation of polynomial, and convert those to value form because it is easy to multiply polynomials in value form. Once we have value form, we'll multiply them. We'll get the result C of x, which is again in value form. And then we'll apply the inverse DFT again in n log n time and get the coefficient form of polynomial C. Right? So this is the whole structure. So we are going to learn DFT and inverse DFT. Right? DFT basically does the evaluation from coefficient to value form. So let's start with the evaluation. That is the most important part. So let's say you are given a polynomial 3 minus 5x plus 2x square minus 3x cube plus x raised to the power 4, and we want it to evaluate it, right? So when we want to convert polynomial in coefficient form to value form, we need to uh, evaluate the polynomial. If it is of degree d, we need to evaluate it on at least d plus 1 points, right? It doesn't matter what points you choose to evaluate the polynomial, right? So we have the freedom to choose which points we want to evaluate this polynomial on, right? So can we choose certain points which enhance the evaluation process or which reduce the overall time? Well, if we take an example, if we pick x is equals to 0, the result is very simple. We don't have to do any calculation at all. The result is directly a0. A0 is the coefficient of x raised to the power 0, right? Similarly, ai is coefficient of x raised to the power I in polynomial, right? So when you are evaluating polynomial on 0, you don't have to do any calculation. You directly get the result, right? Similarly, are there any other properties of any kind that we can use, to just evaluate the polynomial fast, right? Basically, where we know the exact result, what it's going to be. For example, for 0, we already know. So are there any other points? The answer is yes. And let me explain that with an example. So let's say we wanted to evaluate polynomial x square, right? The good thing about this polynomial is that the value of this polynomial on 1 is same as value of this polynomial on minus 1, right? That means p of 1 and p of minus 1 are same. Similarly, p of 2 and p of minus 2 are same. Similarly, p of x and p of minus x are same. That means if you want to evaluate the polynomial on, let's say, 10 different points, just evaluate them, apologies, just evaluate them on half the points, and for the rest half, you already know the result, right? Just evaluate them on 1, 2, 3, 4, and 5, and you already know what will be the result of this polynomial on minus 1, minus 2, minus 3, minus 4, and minus 5. Right? Just by evaluating half the point, you get the whole picture, you get the whole idea, right? So if we can utilize this property to actually evaluate the polynomial that we have, we can do this in half the time, right? We are saving half the time, right? So let's see, can we do that? So this thing, this positive negative pair thing works with polynomial x is equals to, px is equals to x square. Does it work for any other polynomial? Let's see. So if we have polynomial 3 minus x plus x square, and if we try to evaluate it on 1 and minus 1, the values are not same, right? So this optimization that we just saw and we thought we can utilize here in any general polynomial doesn't actually work, right? Why is that so? Why this property of positive and negative pair works on x square and doesn't work on this polynomial? Well, because x square is something called as even function, right? So what is an even function? So even function is a function whose value remains same if you replace the value, if you replace x with minus x. That means f of x is equals to f of minus x. This is called an even function, right? For example, 1 plus 2x squared, this is an even function. No matter whether you evaluate it on 1 or minus 1, the value would not change. This is even function, right? And since we are talking about polynomials, so in context of polynomial, if it has only even degree terms, then it is even function, right? A polynomial which follows properties of even function if the polynomial has only even degree terms. For example, this polynomial, if you see 1 minus 3x square plus x raised to the power 4, it only contains even degree terms, right? Power of x's are all even. So this polynomial is an even polynomial. That means if you evaluate it on 1 and minus 1, the result will not change. All right. So now that we have knowledge of negative positive pair and even function, can we do something about the general polynomial that we have? Well, actually we can do. So what we are going to do, since we know that all the even terms, if a polynomial has only even terms, it is an even function, right? So let's group together the even ones and odd ones. So here we have even degree terms and odd degree terms. This is very easy to separate because all the even degree terms in coefficient form are on the even indices. For example, 0, 2, 4, right? And all the even, odd degree terms are at odd indices 1 and 3. It is very easy to segregate them, right? So now this part of the polynomial is even, but this is not. But we can do that. If you see, here is something in the whole thing, you see there is something common, that is x. If you take it out, this part in the brackets and this part in the brackets, both of them have only even degree terms, right? That means both of these part are actually even function. All right, that means we can apply the even function property here of plus minus pair, right? So in many of the articles that you'll read for FFT, you'll find these two are given special names PE and PO, right? And these two are polynomial of x square, right? PE stands for, of course, even degree terms, and PO stands for odd degree terms. And these two, both of them are actually polynomial of x square, right? Basically 3 times x square raised to the power 0. Let me show you here. So this thing is polynomial of x square. Just to give you an idea, if you see 3 plus 2x square plus x raised to the power 4, you can write it as 3 times x square raised to the power 0 plus 2 times x square raised to the power 1 plus x square raised to the power 2, which basically is the same thing, and it tells you that this is a polynomial of x square. All right. From polynomial of x, we are able to extract two different polynomial of x square which are even function also. And we are doing this segregation so that we can apply the property of positive negative pair so that we can evaluate the polynomial in half the time, right? So till now, everything should be clear. After this, once you have evaluated PE and PO, you can actually evaluate, if you want to evaluate polynomial, original polynomial on some value d, let's say x is equals to z, d, and you want to evaluate P on that, right? P on d and minus d. If you see, P of d would be PE of d square, because x square, right? Plus d times PO of d square, right? From here, we are getting it, right? And if you want to evaluate the original polynomial on minus d, the formula remains almost the same. The plus sign changes to minus because x is replaced with minus d, so it would change to minus d. Nothing changes except this thing, right? For example, PE of d square in both the terms are same. PO of d square in both these equations are same. That means you are evaluating PE and PO one time on d square. You evaluated PE on d square one time. You evaluated PO on d square one time, right? And they are being used in two different equations to evaluate P on two different values. That means you evaluated P and PO on one value, you can use them to evaluate original polynomial on two different values, right? Let me give you an example. This is a very important formula, that's why I've marked it, right? Let me just give you an example. So let's say this is the polynomial. This would be PE. This is PO, right? And let's say if you want to evaluate the original polynomial on 1 minus 1, 2 minus 2, you can do that just by evaluating PE and PO on 1 and 4. 1 is square of 1 minus 1 because P and PO are square of original polynomial, right? My bad. P and PO are polynomial in x square. So if you are evaluating original polynomial on x, these two will be evaluated on x square. So 1 and minus 1 square of both of them is 1, right? And 2 and minus 2 square of both of these is 4. Basically 1 and minus 1 are mapped to 1 and 2 and minus 2 are mapped to 4, right? Now if you see here, just by evaluating PE and PO on 1 and 4, you will be able to evaluate the original polynomial on 1 minus 1, 2 minus 2, because square root of 1 is 1 minus 1. So these two can be evaluated using 1 only, and square root of 4 is 2 minus 2. So I'm showing you. So let's say PE on 1 is 6, PO on 1 is minus 8. I have evaluated these two, right? If I want to evaluate an original polynomial on 1, by the formula that I have marked previously, there's a which is here also. P of 1 would be PE of 1 square plus 1 times PO of 1 square, right? That's I have written here. 1 square, a PE of 1 square. 1 square is 1, so that means PE of 1, which is 6, PO of 1, which is minus 8. Replace both of these two and you will get P1, right? P of 1, which is minus 2. So if you evaluate original polynomial on 1, you'll get minus 2. What if I want to evaluate P on minus 1? Same thing. So if you want to evaluate P on minus 1, the value will be PE of 1 square, PE of minus 1 square, because now we are evaluating original polynomial on minus 1. On 1, we already done. On minus 1, again, you are taking square of that number, right? So square of minus 1 is again going to be 1. Ultimately, you need PE of 1 and PO of 1. Here and also here. You see, you are evaluating PE one time that I did here, but it's being used twice, right? Same goes for PO. So you evaluate these two only once, and these will be used to evaluate two different values of the original polynomial. And there you will get the result 14. So P of minus 1 is 14. You can evaluate and confirm it, right? And why same, right? Because no matter whether you use positive value or negative value, their square will always be positive, right? And same, 1 and minus 1, their square will always be 1. So to evaluate 1, I need P of 1. To evaluate minus 1, again, I need P of 1, right? PE of 1. So that's how when you evaluate PE and PO on one value, its square root is of course two different values. And on those two different values, you can utilize their values to find out, to evaluate basically the original polynomial, right? So the important part is evaluate this one time and it will help you evaluate original polynomial two times, right? So this is how the evaluation works. And one thing we have found that now we can, using the half the values evaluated, we can get the full picture, right? Full points evaluation of the original polynomial. So this is very cool, right? Now if you see what we have been doing, so let's define a function DFT for discrete Fourier transform. It takes a polynomial p in coefficient form and n, the number of points on which you want to evaluate the polynomial, and returns, of course, the value form, right? Basically, it returns value of polynomial p on n different points. That's what we want. That is discrete Fourier transform. So how we are doing it? is this. We want to evaluate p on n different points. So to evaluate it, what we do, we divide polynomial p into two different parts, pe and po, and evaluate these two on n by 2 points, right? Only half the points. Now, after evaluating pe and po on half the points, we'll basically utilize their values using the formula that we have just discussed, and then we'll get the value of p on n different points, right? Using half the values, using n by 2 values, we are getting polynomial p evaluated at n points, right? So what we are doing, we are basically making a recursive call to DFT again, because pe and po are again polynomial and again needs to be evaluated. And who does the job of evaluating a polynomial? DFT. So we'll make, first of all, we'll create from P and PO, and then we'll make recursive call to DFT on PE and PO on n by 2 different points, right? Similarly, this recursive call will keep on happening again and again till we reach the uh, base base case, and then we return the value, and this will be evaluated, right? So we have, it looks like we have built a solution which works in n log n time. Why? See, since each time n will be divided by half, the height won't be more than log n, right? And on each we have n, height is n, and on each stage we are making exactly n calculation. To evaluate p of n, we will make n calculation, and on this stage, on basically this is level 0, this is level 1. On level 1 we have to evaluate two polynomial on n by 2 points. If you combine them, again n calculation will be needed, so on and so forth. On each level we are making exactly n calculation, and there are no more, there are exactly n, sorry, log n height. So the overall computation will be n log n. So this looks like that we have built an n log n solution. All right, but there is an issue. The recursion actually breaks because of the real numbers, and I'll explain you why. All right. So let's say we want to evaluate this polynomial. What we'll do, we'll make a DFT call to polynomial and pass n, that we want to evaluate this polynomial on n different points, right? That DFT, what it does, it divides polynomial in even and odd terms and evaluate, that gives us two different polynomials of degree n by 2, right? And then we evaluate those recursively. I'll only talk about PE here because I have to show the whole call hierarchy and what happens. So we'll make a recursive, we'll basically make a call to DFT, passing the original polynomial and n. What this function will do, it will take PE and PO and only show PE, which is polynomial of x square, and it looks something like this, right? We need to evaluate this, so this will make a recursive call to DFT of P of x square, which is basically this, and this needs to be evaluated on n by 2 points, right? Similarly, this is again a polynomial who needs to be evaluated, and we are not on the base case, right? Base case will be when you have only one element in your polynomial, right? So one element, that means basically this only coefficient of x raised to power 0. Nothing needs to be evaluated there, so you can return direct that, right? So we are not on base case. Again, this will be divided into different polynomials, and again PE of this would look something like this. Again, take the even terms, uh, yeah, even degree terms. So 3 plus x raised to power 4. So we'll make a DFT call to p of x raised to power 4, which basically represents this polynomial, which is of polynomial of x raised to power 4. Each time when you are sending the polynomial, it degree just it will be of square of previous one. So basically this is polynomial of x, this is polynomial of x square, this is polynomial of x raised to power 4, so on and so forth, right? So this is polynomial of degree 4, x raised to power 4, not degree 4, x raised to power 4. And we make a recursive call to DFT p of x raised to power 4 n by 4, because this needs to be evaluated on n by 4 different points, right? So this is how the calls happen in the recursion that we just built. The issue here is that here I need to evaluate this polynomial on n points, and we are taking advantage of plus minus pairs, right? I need, let's say this polynomial to be evaluated on 4 different points, so I can choose 1 minus 1, 2 minus 2, right? Now, since the we have made a recursive call and this is a polynomial of x square, this only needs to be evaluated on n by 2 points. This I want to be evaluated in 4 points, so this needs to be evaluated on 2 points only, right? And those 2 points will be square of these. Square of 1 minus 1 is same number, that is 1. Square of 2 and minus 2 is same number, which is 4. So evaluate this only on 1 and 4. So square root of 1 is 1 minus 1. So this will help evaluate original polynomial on 1 minus 1. This will help evaluate original polynomial on 2n minus 2. Great thing, because of the square root we get a positive negative pair, and that's exactly what we are doing here. So on level 1 and level 2 things are fine, but when we make a DFT call to this to evaluate this polynomial, I wanted this to be evaluated on 4 points. That means this needs to be evaluated on 2 points. That means this needs to be evaluated on 1 point, right? So what value would you choose here whose square root is 1 and 4? First of all, we are not even getting a positive negative pair here, right? Because square of all of these will be positive only. So on level 2, this is level 1, this is level 2 of function calls. On level 2, all of the values are actually positive. If all of the values are positive on which the polynomial needs to be evaluated, how in the next step we are going to take advantage of positive negative pair? Here all of the values are not positive but in pairs of positive negative. That's why in the next stage we are able to evaluate only half points and take advantage of their square root, right? But here if all of the values are positive, what value would you evaluate this polynomial on so that its square root are these two? Not possible. Square root of every single number will be positive negative, right? But because we are squaring each term from level 1 to level 2, on level 2 we'll always have all the values positive. That means third level we won't be able to apply the recursion, and hence recursion breaks here because of the real numbers, right? Because square root of this is positive negative, square root of this is positive negative, that's fine. But what number you will choose here so that square root of that number is 1 and 4? Not possible. So that's why when you are working with real numbers, this recursion actually breaks and doesn't work. We need on each different level number such that their square root map to two different values on the previous level. That's how recursion works, the way we have built it, right? So real number does not provide that. That's why we need to yeah, you remember this is the original formula, and using one value on a certain level we are able to evaluate the previous level on two different values using this formula, right? Because of the square, and square root of this d square will be plus and minus d. That's why, right? But again here, if you, since on level 2 everything is positive, on level 3 you won't be able to find a number whose square root will map to two different values on level 2. That's why on real numbers this recursion actually breaks, but this doesn't break with complex numbers. I'll explain it in a moment. So just to give you an idea, this is a 7-degree polynomial. That means we need to evaluate this polynomial on eight different values, right? That's why I've chosen eight different values: 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, right? On the next level you can evaluate the next polynomial, that is PE, on 4 different values, half of the previous one, right? That would be square of 1 minus 1, that is 1 square, 2 square, 3 square, and 4 square, right? So you evaluate this on 2 square and original polynomial will be able to be basically this will help evaluate the original polynomial on 2n minus 2. Simple enough. But when we go again to the third level, you won't be able to find any integer whose square root is 1 and 4, or any integer whose square root is 9 and 16. So recursion breaks here. And just to move ahead with a solution, we can actually utilize complex numbers, and to be precise, roots of unity. So instead of using plus minus 1, plus minus 1, plus minus 2, plus minus 3, what we are going to do, we are going to utilize the complex numbers. right? So you remember we were not able to go to the third level, right? But here we will be able to. Let's say I wanted to evaluate this only on 4 different values. I will evaluate this polynomial on 1 minus 1, I minus I, where I is the imaginary number, right? So if we see square of 1 minus 1 is 1, or you can work it backwards, square root of 1 is 1 minus 1, right? Similarly, square of I is minus 1, square of minus I is again minus 1, or basically square root of minus 1 is I and minus I. See, so from level 1 we reached level 2, which we were also able to do with the real numbers. But here's the important part. Here we are also able to go to the third level. That means what number do you choose here? You get 1 minus 1. Of course, 1, because square of 1 is 1 and square of minus 1 is also 1. So you can see we are able to get to the third level. And just to give you a better idea, try to repeat the same example with n is equals to 8, right? Try to replicate the same example with 8 different values, and you'll still find that we are able to do it. But the question you'll ask yourself is, how do we decide what values to choose here? Earlier, when we were choosing the values to evaluate the actual polynomial, we started with 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, right? It seems like I have picked the random numbers here. How do you know that 8 numbers that you need to pick and move ahead in the hierarchy, what are the initial numbers? So you see, these are not random numbers actually, right? These are what we call roots of unity. So what is a root of unity? Very simple, one line definition. So solution of an equation x raised to power 1 is equals to, yeah, x raised to power n is equals to 1. Solution of this equation is called roots of unity, right? So if n is, let's say, 4, so x raised to power 4 is equals to 1. Again, the solution of that equation, there will be 4 solutions, right? Uh, those will be known as roots of unity for that equation, right? So as simple as that, that is roots of unity. So if you see, the 4 points that I've chosen are not random. Actually, solution of equation x raised to power 4. So x raised to power 4 is equals to 1. We'll have 4 solutions, and those 4 solutions will be 1 minus 1, I minus I, right? Similarly, these are not random number. These are solution of equation x square is equals to 1. Why square? Because we need 2 points here, we needed 4 points here, and finally we need 1 point here, which will be solution of x raised to power 1 is equals to 1. So see, on each point, we are not just picking random numbers, but roots of unity. So if I'm giving you an example, if I'm giving you an exercise to repeat the same thing that I've done here and go to one more level, you will start with x raised to power 8, because you need 8 different points. So x raised to power 8 is equals to 1. There will be 8 different solutions. Those 8 solutions will form your initial point to evaluate the polynomial, right? And you'll see that it works perfectly. And we have solved the issue that we face with the real numbers, that on the next stage, that means level 2 of recursive call, all of the numbers were positive. When you work with complex number, that doesn't happen. On the next level also, you will always get plus minus pairs, right? So yeah, I'll stop here, and why that happens I'll explain in the next lecture, because this lecture has already gone too large, right? Because I had to explain so many things. So let's stop here, and then next lecture I'll explain how, first of all, how you come up with the numbers and the solution. I mean, even though you know that the initial numbers will be, for example, x raised to power 8 is equals to 1, will give you 8 solution. How do you know the exact value of those? Because you need those points to evaluate the polynomial, right? So you need to know the solution. How do you know that? I'll explain that in the next lecture, which is the solution of basically the roots of unity, and that is very easy to calculate, right? And I'll also give you a little more detail of why we always get positive negative pair if we keep on squaring the original numbers, right? Basically we have squared 1 and minus 1 to get 1, right? And I and minus I to get minus 1. We are getting positive negative pair. Again, if you square them, you will get positive negative pairs if this was one level ahead, right? We are using an example which goes through 3 levels only. when you take x is equals to 8, sorry, n is equals to 8, you will get one more level, and you will see that yes, on each different level you will always get positive negative pair. Why does that happen? I'll explain that in the next lecture, and in the next lecture also we are going to build the overall algorithm, right? And after that we are actually going to code it and finally solve some problems, right? So yeah, this is it for this lecture. I know this is very complex, confusing, and hard to understand. I understand that. So if you have any issue and you are not able to understand, please let me know in the comment section. I'll try to address those issues in the next lecture. All right. So yeah, this is it for this lecture. Let's meet again in the next lecture. And till then, keep coding. Thank you.